going to present you on the project of necessity versus correlation in biological science. First, correlation means two things vary together, but neither is proven to cause the other. When the neuron fires every time you remember something, that's a correlation. Necessity means without this component, the function cannot happen. We establish necessity by removing or silencing something. If the behavior disappeared, it was necessary. Sufficiency means activating this component alone is enough to produce the function. We establish sufficiency by artificially turning something on. If the behavior appears, it was sufficient. Here's the critical constraint. Purely observational methods like fMRI, EEG, or calcium imaging cannot test necessity or sufficiency. They can only tell you that two things co-occur. To make a causal claim, however, you need a manipulation. Keep that in mind. We will return to it. This brings me to my two research questions. The first is a correlational question. Does the hippocampal activity at the moment of encoding predict a memory will survive 24 hours later? Notice the question is asking whether a neural pattern co-occurs with later success. It's not asking whether a pattern caused the success. So this question is correlational. The second question is a necessity one. Is hippocampal network activity during sleep causally required for overnight memory consolidation? This question is asking whether removing something causes consolidation to fail. Here, manipulation is required, and we aim to test for necessity of hippocampal network activity for memory consolidation. Now, let me walk you through each one. First, study 1 uses fMRI with subsequent memory paradigm. 36 healthy adults encode 120 word scene pairs while lying in the scanner. The key feature of this paradigm is that trials are classified retrospectively after each experiment, based on what the participant actually remembered 24 hours later. Remembered trials versus forgotten trials. The contrast is subsequent memory effect, and it is a measure of interest. Two controls are essential here. First, an embedded two-back working memory task runs during encoding. Participants judge whether each word matched the 1-2 item prior. This forces all participants to process stimuli at the same depth and prevents some deliberately rehearsing while others passively view. Without this, difference in encoding strategy would be an alternative explanation for any other neural differences we observe. So this control an encoding depth confound and supports internal validity. Second, stimuli are counterbalanced across two lists using a Latin square. Each word scene pair appears in the context condition for half the participant and in no context baseline condition for the other half. This controls item level imaginability and word frequency. Otherwise, memorable words would cluster in one condition and drive the result. Participants are blinded to the hypothesis. No placebo is needed because nothing is administered. The dependent variable is operationalized as hippocampal bold signal for subsequent recalled item minus hippocampal bold signal for subsequent forgotten items, estimated via single trial general linear models. A positive subsequent memory effect in the context condition but no context baseline will be indicative of our core result because the pattern attributes to the predictive signal to the context-dependent encoding specifically, not simply to the general attention or arousal. Here's the question study 1 leaves open. We find that hippocampal encoding activity predicts later recall, but what happens after encoding? The memory has to survive overnight, and the leading account of how it survives involves sleep, specifically a process during non-REM sleep in which the hippocampus replays the day's experiences and coordinates transfer to long-term cortical storage. This replay is driven by sharp wave ripples. In rodents, surprising sharp wave ripples during sleep impairs next-day spatial memory. But the question is whether we can test the same logic in healthy human non-invasively. In fact, we can, and that brings us to study 2. The method we are using is 1 Hz inhibitory repetitive TMS, or we call it rTMS, applied to the lateral parietal cortex immediately before sleep. The hippocampus is too deep for direct TMS targeting, so we are targeting at this primary neocortical network node, a region with high resting state functional connectivity to hippocampus, which transiently suppress hippocampal network activity during early non-REM consolidation window. 30 participants encode word-image pairs in the evening, taking an immediate recall test to establish an encoding baseline, receiving either active or sham rTMS, sleep for 8 hours under polysomnographic monitoring, then complete a morning recall task. The design is within subject crossover. Every participant completes both conditions separated by 2 weeks washout. And this eliminates routine person memory ability as a confound and gives us the statistical power to detect consolidation difference that the between subject design would obscure. And 3 controls are essential. First is the change score as the dependent variable. Morning recall minus pre-sleep recall. Without the pre-sleep baseline, we cannot separate what sleep did from what encoding produced, and this change score isolates the consolidation. The second is the sham condition, in which a tilt coil rotated 90 degrees from scalp, producing identical auditory and tactile sensation with no transcranial field. Without a perceptually matched sham, any memory difference between the session could reflect the sound of the coil or expectation effects rather than cortical disruption. Participants cannot distinguish active from sham, and this is double-blind. The experimenter scoring the morning test also has no access to the session type, so as the participant themselves. And the third is polysomnography throughout the sleep. If active rTMS reduced total non-REM sleep duration, any memory impairment is explained by sleep loss, not only hippocampal network disruption. So PSG rules out that, and non-REM sleep duration is entered as a covariate. If active rTMS produce a significantly lower change score than sham, with equivalent encoding baseline and equivalent non-REM sleep duration, then we can confidently conclude that hippocampal network activity during sleep was causally necessary for overnight consolidation. Overall, in real science, we often combine both approach, whether it's manipulative or observational. We test both necessity and correlation. Correlation told the field where to look at, and manipulation study told the field what is actually happening.